So, yeah, I kind of was mentioning a little bit. We kind of missed that Friday where I normally would talk about topics 13, and we were going to talk about topic 12 more statistical distributions. I'm going to go through that very quickly. I might even put in the playlist just the recordings I shared. That way you all can like kind of like just watch those recordings, like if you need to catch up in the playlist. So I might put that in there, but I highly recommend going through those recordings for, the past me talking about that same subject. But I'll at least go through it very quickly today, and then you guys can stop me if something feels like really like you feel lost in it. So let me go and share my screen, and we'll go right into that section. And then afterwards, we'll actually go into topic 15, which will be, topic 14, which will be hypothesis testing. And over the next couple of days, I'm going to kind of like combine topics 14, 15, and 16, which will be A/B testing, kind of together just to kind of like I think they kind of blend well together. So I won't have it very strict and like, oh, this is topic 16, this is topic 14 or whatever. Okay, but first let's talk about statistical distributions. I think I showed you all some of this a little bit like back on Wednesday of last week, right? It's been a long while. But you can see we talked about normal distribution. Livia talked about that last time. And this is a specific equation, kind of showed you this. The mean and standard deviation is mu and sigma. That's the classic sample or population mean. And then the standard deviation is the population standard deviation. So with those two values, you can define any normal distribution, Gaussian distribution, it's the same thing, bell curve, right? Okay, so there's a couple other ones that you should kind of be aware of. I'm going to really point out the ones that I think that are important that you should know as a data scientist. Is one is the binomial distribution. So binomial distribution, basically, you can think of like probably of getting so many successes in a given number of trials. Basically saying, have you had a success or not? And so there's actually some useful equations to getting the mean from this probability distribution. So if we actually have the probability distribution, we can actually get the mean just basically n times p. So n being the number of trials, lowercase p here being the percentage of success. And the standard deviation can actually be given out by simply this equation here. I won't go into the full details. Most of this stuff can be actually found on Wikipedia, which is kind of nice. So I kind of have these links here as well. So point probability, all that good stuff. So other statistical distributions, uniform distribution, which basically is just saying like everything is equal. So think of like a roll of a die. Basically 1, 2, 3, 4, 5, 6 are all equal to each other. So uniform distribution is pretty kind of like straightforward. There's a negative binomial distribution, geometric, Poisson distribution, exponential distribution. I would say that the three that are most common besides the bell curve are probably binomial, Poisson distribution, and exponential distribution. Those are the ones, and the reason why I say more common is that if you know that distribution exists and what situations it is, you can apply that distribution to, hey, like this is what the data should look like, and actually apply essentially the equation to it. Like saying, okay, look, we know these values aren't here. Let's build up a model of this equation and actually simulate or get an idea of what we would expect. Okay, so and I'm going to go by really quickly. So I have a few lists of these distributions here. Uniform distributions, basically it's like what this will look like essentially is, I think I showed this maybe even last time, but I just draw it really quickly here. Is it looks something along this way where basically if you have a histogram or like kind of like your PMF, right? It basically is that everything is equal. So like imagine this is the probability of rolling a 1, probability of rolling a 2, probability of rolling a 3. It's all equal. Essentially, it looks like a big rectangle, and where each line basically would represent, in this case, discrete probability. So 1, 2, 3, 4, 5, and 6. If this was continuous, let's say, for example, choosing a number between 0 and 1 by a computer, every number is probable. This would still have the same shape here. So it's actually pretty easy. The mean basically is going from here to here. So like, for example, if you roll the die, 100 times, you probably would get a mean about, about 3.5, like, about 3.5, right? Because you can get 1, 2, 3, 4, 5, 6. So you probably get about here. Sometimes you get 1, sometimes you get 6, and sometimes you get 3, and it kind of evens out to be about halfway. Okay. So that is the uniform distribution. Nothing too exciting about it, but it's the basis of a lot of distributions that we will create. So it's useful to know that it exists. Negative binomial distribution. This one's a little harder to kind of explain. I think a lot of people have their head kind of wrap around this. Basically, the idea here is the binomial distribution is like if you flip the coin n times, your success, like how many probability of having so many successes. So if I flip it like, 10 times, I get 3 heads. What's that probability? You can figure that out. The negative binomial distribution is a little bit different. You flip the coin until you have a stopping condition. So for example, my stopping condition could be flip the coin until you get 2 heads, like in total, or sorry, 2 tails. I think I put it right here. So you flip the coin, you get heads. You flip the coin, you get heads. You flip the coin, you get tails. Like, okay, there's 1 tails. Flip the coin again, you get heads. Flip the coin, you get another heads. Flip the coin again, you get another tails. Okay, and that would be when you stop doing your trials. So the idea there is saying, what's the probability of how long can my run go? So technically your run can go infinitely long, right? For the binomial distribution, you're limited in how many successes you can have because you only have so many trials, right? Or how many flips. So you can technically flip a coin forever and never get 2 tails in total. But you can probably guess that's very, very unlikely. And that's what the negative binomial distribution is. There's some useful equations. You can look this up. But the main thing is the idea is that you can adjust saying, what's the likelihood of you getting this stopping condition and all that good stuff. Okay, does that make sense to people? At least the concept of that negative binomial distribution. Okay, cool. A classic one of this is like, like how does this apply? Everyone says like, you talk about coin flips, Victor, but like how does this apply to like real data science stuff? This would be similar to like a stopping condition be like, oh, someone, for example, subscribed to a newsletter after visiting the website for so long, like where do they stop? Obviously, this is going to be discrete. And the opposite of this guy right here on the continuous side would be closer to the Poisson distribution. Okay. Cool, makes sense? Yeah. Okay. Geometric distribution. This is basically the negative binomial, but it stops after the first failure. Basically, I don't even talk about this. It's essentially this literal thing, except that you stop after the first failure. So in this case, 1 failure is a tail, tails. So it gets its special name because it's a special one, like it's the first failure, but it really is just a negative binomial distribution. So I don't even talk about it. Poisson distribution. This is kind of like I said, it's kind of like the continuous version of this. Is the probability of having the number of occurrences or successes in a given time interval or space. So a classic one of this is how many people will walk through the store over the next 30 minutes. And that's kind of the idea of saying, okay, like there's a continued amount of time. There's a probability of having, 29 people walk in the store or 30 people walk through the store. What's the chances of this happening? And you can use prior data to kind of get this distribution. Again, more information here. This is a very classic one. Exponential distribution at this point, I think with the coronavirus, we're maybe a little more familiar with some exponentials that are like larger than a growth larger than 1. So this is kind of classic, but usually besides those other parts, you actually talk about decaying factors too. So kind of saying like, there's going to be eventually a decay over time. So like a classic of this is like particle decay, but you can apply for things that basically over time you would expect decay. So this is actually something that the coronavirus right now is that we expect, if everyone's familiar with R naught, the R factor for coronavirus, or I should say COVID-19 really specifically, but like the idea is that we wanted that less than 1 and that eventually the numbers would go down for the number of people who would be infected continuously and then overall collectively, since each person who was infected could potentially infect someone else. So we actually can use this to help predict, how long it will take to actually for essentially, in this case, coronavirus or COVID-19 to be essentially like extinct or effectively extinct, where it's not going to be being passed around very much. So these are, again, really common. Exponential. Poisson is very common too in the binomial distribution. Okay. Sound pretty good? I know I went to that very, very quickly, but hopefully you get an idea that there's some distributions in here.
Just a quick question, like what does lambda stand for in these cases?
Yeah, this lambda right here basically is kind of like this decay factor. So this is a different, it's separate from the actual, it's usually not defined by the mean or standard deviation, but you can pull the standard deviation in the mean from this. But basically it's saying like how do I say this? Like, what is its growth factor? Like, does it increase, like you can kind of think it's related to like when we talk about the coronavirus, like, oh, like the R factor. I'm not a virologist or epidemiologist or anything like that, but my understanding of it's like, oh, that's supposed to represent like how many other people from every 1 person infected, how many more people that are getting infected. That's kind of equivalent to this lambda factor. It's like how much does it grow by or how much does it shrink by? Okay. Cool. Does that make sense, Dave?
Yeah. So in this last case, it's like a half-life.
Exactly. This is actually where half-life comes from, is that you can define, this is not literally the equation you plug in for half-life, but you can define your lambda of saying how long would it take for half of the values talk about half-life, how long half the particles take to decay completely, versus lambda is really focusing on what's the probability of this one particle decaying. So that's kind of like this like growth factor. It's kind of more individual centric versus like overall distribution centric, if that makes sense. But it's related. You could definitely find it from here. Okay. Cool. All right. I'll move on then from statistical distributions. There's more in the curriculum, but I just wanted to show you all a little bit about this. The big thing I want you to take it from this distribution is that if you know the situation of like what the situation calls for, you can predict what the distribution is going to look like, and then use that prediction to basically get an idea of, when you get a value, does this seem reasonable, or is the situation different from what you initially identified it as? So that's really what the distribution is really useful for. Okay. So yeah, so anyway, that's just distributions. Big one you should really focus on is the normal distribution. I do have this little notebook for sampling. So one thing I kind of talk about, like we're not going to go through this whole thing, but like when you do a random sample or to talk about sampling, you always have to be very careful with how the data comes out, because you will get data, but you should always be familiar with like how were these data collected, like what was the method put in, and that can greatly affect what that means for your sample. Anyone's heard of like random sample? Like we say like a random sample. Yeah, so random sample is usually kind of like what we talk about, like random, for example, in the medical field, random controlled trials. Basically, the idea there is that when you pick someone out, they are uniformly sampled across the population. So any one person ideally should be have an equal chance of being chosen. Now, as you can probably guess, that's actually very, very hard to do. How do you make sure, let's say you're studying the United States, how do you make sure that 300 plus million people in the United States have an equal chance of being picked? That's actually quite hard to do. Does anyone know like what they classically have done to try to randomly sample across all the United States, for example? No, that's different actually from the census, because census actually does try to get everyone. Yeah, so one classic they've done is phone calls. Is you basically make a phone call because the idea is everyone has a phone. Well, first of all, you can see this might not actually be true for some level. And one interesting thing is they used to use landlines, which, as we can kind of tell now, I don't have a landline. There's plenty of people who don't actually have landlines anymore. In fact, most people I know who have landlines usually never answer the phone because they're like, my phone's not there. And then plus there's also, I don't know about you all, but I don't answer my phone if I don't really recognize the number, or maybe sometimes I do, but like I kind of screen my calls, right? So there's also some bias in there. So it's actually very difficult to perform a random sample. One other way of sampling is something called stratified samples. Is anyone familiar with that term when you say stratified samples? So in that case, you actually look at the population. Let's say, for example, you look at saying a school, like this is one of my classics, like you have a school of like first, second, third, fourth, fifth graders, right? A random sample would be like you pick out people randomly from the school, and so each student has an equal amount of chance of being picked. But let's pretend, for example, the second grade class has only 5 people in it. It's like a really, 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 really small class. But then the rest of the school has like 30 people per grade. Well, the problem is like you randomly sample, you might actually miss the second graders, which you might identify as being actually an important part of your survey. So what you can do is a stratified sample where each person in each stratum, each group, has an equal chance of being picked, but you make sure that you have a certain portion of second graders and a certain portion of first graders in your total sample. So the idea there is to make sure that you don't leave out smaller groups that would have not been randomly sampled. Okay, does that make sense? All right. I was just showing really quickly, like, some coding examples. We have this data Titanic data set, if anyone's familiar, pretty common one. I'm not going to go through all of this data, but you can see here, I can, for example, take the average of all the ages. So I take the ages of every person in this case. How many ages are there? 714 people. So I'm just graphing all the NA. And you can see the average here for all 714 people was about 29.7. So one way you could try to figure out the population mean is to get every single person and actually measure, whatever thing that you care about. Of course, that's actually very expensive and very difficult to do. That's actually one of the reasons why the US Census can be very expensive, is that trying to get every single person, including the people who try to avoid you or don't try to put in information, by law, actually, by census, they actually have to like get everyone as much as possible. It's really interesting, but it's actually very expensive, which is why they only do it like every 10 years. So another way you can do this is sampling. So in this case, I'm actually going to sample 100 different people. Note that I just put a random state to make sure it's consistent. And then say, oh, let me go ahead and sample, take the average, the mean of that sample. And when I do this, oops, first of all, I don't have this mean defined. What? Did I define it somewhere else? Oh, it's called mean s. No. It should be age mean. Sorry, I don't know what happened with. There we go. So you can see here, this was the age mean here, was this one referencing like the total population. And you can see that the sample mean was 28.7, which isn't quite true of the total population, but it's a percent error of like 3%, about 3%. So it's not too far off, like it seems reasonable. Like if someone said the average was 28.7 and someone said, says the actual is 29.7, I'd say that's pretty close, especially for only 714 people. So that's the idea of this random sample. Okay, is that you don't have to look at everyone. You can look at a smaller portion. Okay, cool. Does that make sense to people? Any questions about that? Very quick, like me going through. Okay, two takeaways I want you to take away from this is, one, be careful how you sample, because your sample can, your data, even though you think it's random sample or stratified sample, to be very careful with how you collect that data, or at least know how the data was collected. And two, you can get ideas of the full population by looking at a smaller portion, a sample of that total population. But that's actually where confidence intervals will actually take a huge role in this. Okay, so let's see here, moving on. Good, we're still under 15 minutes. I was hoping that we were going to be under 15 minutes, so I think we're still good. All right, so I kind of mentioned about sampling, so I kind of use this example again. I just want to show you this case. This is the same data, but you can see here there's a distribution. So you can see actually there's a few younger people, and then it spikes up over to this larger value between like 20 and 30 years old, and then it kind of teeters out. So you can kind of imagine where the sample, that average probably be about right here, which is 29.7, right? So that's kind of makes sense. If I take a random sample, doing this, you can see, there we go, 28.7. So this is literally what we just showed, right? So the problem with this is like the chances are is that we might sample like this sample right here when we like random take 100 people. It's possible that we get a bunch of very older people and it would skew our sample, or get a lot of younger people and skew our sample, right? And that would tell us like oh, like, like we would say, let's say we got like, by just pure chance, we randomly sampled and we ended up getting about like these people here, and we said the average age is 65 years old, and it's like, well, that's clearly really off. Like but that's a chance, right? When we take random people. So the thing is, like, we want to know a little bit, like, well, how likely would that have happened? And the idea here is that we might not actually know what the true population looks like. So we kind of want to get an idea of, like, from our sample, we collect 100 people, look at their average and say, okay, how likely is this true? And that's actually a really tough thing to do. And it turns out we can't actually tell information about this. And this is actually where the central limit theorem will come into play. But to show a little bit like what this means, imagine instead of me taking one random sample and then looking at that mean, let me pretend I take a bunch of different random samples. Remember, each person is equally likely to be pulled in, and look what the average, what the mean age will be. Does that make sense? So I'm going to just randomly sample and say, sometimes I'm going to get, people kind of spread out evenly, which is closer to what we want, but sometimes I'm going to get some people more on the extreme ends. And just looking at what that distribution looks like. So what this code looks like right here is that for each I in 10 to the power of 3, so this is 1,000 different times I'm going to sample. I'm going to get 1,000 different samples. What I'm going to do is say, okay, I'm going to take my first sample. I'm going to say, okay, 100 people in this case. So number of people, I think was 100. Yeah, 100 people. I'm going to sample 100 people. And then I'm going to do the calculate the average of that sample and add it into a list of all my samples means. Does that make sense? So my first time I do this, I'm going to pull 100 people and say, oh, the average age is 20 years old. And then I'm going to put that in a list. And then I'm going to do it again and randomly sample another time 100 different people. Note that's the same out of 714. So I'm just doing another random 100 100 people, and then calculate that mean, and then add that to my list, and just keep doing that 1,000 times. Does that make sense to people? Okay, so then it's like, okay, like if I looked at then all these samples, what does that distribution look like, right? And so I kind of want you to remember back, this is what the actual distribution looks like of the population, right, of the ages. But when we do this 1,000 times, we can actually see that we get this distribution right here. And you can see that sometimes I get some very low ages, like maybe closer to almost like 25 and a half, right? Is my like lowest age right here of the average. And sometimes I get a sample and their average age is like 34, which is not too far off. You know, neither of these values are too far off, but the real average is probably closer to like, you know, like, well, we already looked it up. The real average is like close to 30 years old, right? 29.7. So you can see a little bit is like, we kind of mostly got values that are pretty close to that average right here. And then sometimes we got some extremes over here. And if you look at this shape, you can see me kind of, looks familiar. What does this look like when we look at this like overall shape?
Normal distribution.
It looks like a normal distribution, a Gaussian, right? And that's kind of, I think that might be a little unexpected when you think about it, because this was not normal distribution, right? Like you wouldn't necessarily expect to pull that. But it turns out is that if we sample multiple times and look at those means, we actually get a normal distribution. In fact, you can kind of see a little bit, this is exactly what the central limit theorem is. But you can see a little bit too, is like, okay, what if we took the sample of these sample means? Like, okay, what would be the average of all these samples? And you actually turned out it's actually pretty close. Like 26, the mean of the sample means was 29.698. I actually had to add extra decimals because I think this ended up being 29.7. I had to add this little extra decimal to see that little extra the difference between these two. And you can see that actually the mean of the sample means is actually very close to the average, which kind of makes sense, I think. Hopefully you can see like why that would be true. But this is actually the power of the central limit theorem. And so also abbreviated CLT. Basically, this is saying that, hey, if we take many samples and look at some statistic, in this case we talk about mean, but it could be anything really. If we look at the sample statistic, that we actually approach a normal curve. And so with that, it doesn't tell us what the actual mean is, but it means that when we pull a sample, we likely will fall within this area that's within one standard deviation of the true population mean. In this case, the true population mean is represented with a mu. And usually we talk about like the average is like X bar or something that's not mu. So usually we're talking about basically, oh, a single sample, it's not going to be the population mean, but it might be close. And in fact, it's probably about 69% of the time within this area. And that's actually where we get the central limit theorems is, hey, like if you did this a bunch of times, this experiment, you likely will be in here. So sometimes we'll get the sample and we'll get over here. We don't know if that was right or not, but it becomes increasingly unlikely for us to get very, very far off into these more extreme values. Does that make sense to people? Give me a thumbs up if that made sense. Thumbs down, you're like sideways. Like, Okay, I saw most people kind of go thumbs up, maybe sideways a little bit. The main thing you should know is that when we do a sample, when we actually take one sample, we can expect that it will be one of these samples, the samples that are very close to the center. And because of that, we can estimate the probability of us actually, well, not estimate the probability, we can estimate how likely it is for us to fall in that range and how likely it's actually we got the true population mean. If I were to increase this value, just to kind of show you all, like I could do this infinitely, right? Of course, my computer can only do so much. So this is 10,000 times, but you can see it gets very close to a normal curve. But also note that sometimes we do get more of those extreme values. Last time I only went up to like 25 and a half. This is close to 24. So you can see is that still majority of them are very close to the actual mean. And with that, we can actually build up our confidence intervals. That's really what a confidence interval is telling you. It's not saying anything specifically about like the sample you have. Like, it's not really talking about how likely you get in here. It's basically saying like, hey, like, what is the range that we would expect to get the sample in? And that's kind of the idea. Is like if you randomly sample across this full population of all possible samples, this is how likely you would get this value. So again, I'm not going to go into full details here on the confidence interval, but I wanted to show one kind of quick thing is that usually the incorrect interpretation of a confidence interval is there's a 95% probability that the mean age is between 26.3 and 28.3. So for the record, you can actually calculate the confidence interval like within one line. Like it's very quick to calculate, but usually people interpret it wrong. This is not technically true. So there's a probably 95% probability that the mean age is between 26.3 and 28.3. It's not really right interpretation. The correct interpretation is if we find, let's say, 100 random samples and create confidence intervals, we expect 95 intervals to contain the true mean of the population. So when we actually say, okay, here is our sample mean, here's our confidence interval, we basically are saying this constant confidence interval, if we were to repeat this process, 95% of those intervals would actually contain the true population mean. It's a subtle difference, but it does help because sometimes people think that they're like, oh, if they get a sample mean, that they're 95% likely for them to actually have the true population mean. It's not quite right. It's technically saying that we have this, we have this process that we could have been really, really lucky or unlucky, however you see it. But we believe that we're probably one of the 95 intervals in this case. So note that basically to have a larger confidence interval, it means that you basically have to expand out what the values possibly are. Because if you expand out your confidence interval, then it's more likely that your intervals will actually contain, more of your confidence intervals will actually contain true population mean. So just to show a little bit of like kind of using the same data, the Titanic data, we can see here in this case, I did a little disk plot. You can see a little bit of the distribution. It's a little bit different because I just changed out the bins, but you can see like about the same. And I do a sample in this case of 10 people, right? And so with those 10 people, I could say, okay, go ahead and just try out like trying to get like a random set of 10 people and just do it a bunch of times, essentially is what this is doing. So I do this a bunch of times, and then each time, each of these numbers is actually one sample mean. So you can see this basically repeated over and over and over and over again. And with that value, you can actually see, it's like, okay, how likely would each of those means be? And you can actually see it's very close, in this case, in the red, is the true mean. And you can see, like, it's kind of hard to tell in here because it's so close together. But you can see they're actually very, very bunched up, and they're likely to be near that true mean. And so that's actually the idea there. It's like, oh, we now have that true mean. And then what we can do is actually find the confidence interval. Now, because confidence interval is defined by essentially saying, hey, if we just do a sample a bunch of times, how likely would our sample contain this value? We can actually do something called bootstrap. I'm not going to go into the full details because we just don't have enough time. We could use bootstrap to basically pull this in and say, okay, like let me just try to do this over and over again. And you can see here is that we actually get something that's very, very close. And we actually can calculate our standard deviation from this distribution. And because this distribution is just easy to find, because we already know what we expect that distribution to look like, we can say, hey, okay, how many times did I actually sample this, and calculate the standard deviation. And we say, okay, like let's say two standard deviations usually at our confidence interval. Well, two standard deviations from our, remember our, was it our 68, 95, 99 rule? Well, we know that basically 95% of the values would be contained within two standard deviations of this normal distribution. So we just subtract off two standard deviations from our sample mean. Note that this is just our sample mean, not the true population mean. So remember, our sample mean in this case is 26.8. And we say from 21.8 to 31.8, we are within two standard deviations within like our mean, or our sample mean. That's going to be our 95% confidence interval. Okay. Now, this is like the really like long way to do it. Like you could do it this way, but this can actually like, you know, like I think it's a little overkill. Typically what you'll do is, for example, in my case, I use SciPy more than stats models. You can do something similar to stats models, but importing this SciPy.stats, which is just a library, and just saying, okay, from SciPy.stats.norm, and basically say, okay, here is my average. I'm going to say my average is my sample means. My standard deviation is my sample means from here. And I can actually find from the normal curve.cdf and a normal curve CDF of 20, you can basically derive a confidence interval of saying like how far apart those things are. If I had, for example, here, I believe if I do 31, 21, I should get about 95. Yeah. So basically it's showing a little bit like where this confidence interval comes from. But typically you can actually just calculate this value and say, okay, from our sample mean, you can actually directly say, okay, this plug in this formula and get the confidence interval for that sample. Okay. Cool. All right, I went through stuff really quickly, so I know not every, I don't expect everyone to be like, yes, I understand everything that I talked about. But overall, how do we feel about like this idea of this confidence interval and then actually using the mean from the sample? Okay, so my suggestion to you is watch the recordings that I've done. Also look at the material, and then also come back with questions, especially during office hours, and we can always like go over stuff. Okay, cool. All right, so that was the end of topic like 12 and 13 rapid fire. I went a little bit longer than 15 minutes than I expected, but that's okay. Hopefully you guys found that useful. So we'll go into now hypothesis testing.